we're going to talk about the electromagnetic spectrum. The electromagnetic spectrum refers to all types of electromagnetic radiation. That includes visible light, which we now know as an electromagnetic wave, as well as other forms of electromagnetic radiation, some of which can be made easily in a laboratory setting with the right electronic equipment like radio and television broadcast waves, and other types that occur only in things like nuclear reactions. We know at this point, like I say, that light is in fact an electromagnetic wave. Visible light has a wavelength between 400 and 700 nanometers, or really 750 nanometers. Let's look though, before we talk very much about light itself, about the whole spectrum. If we think in terms of wavelengths, we measure wavelengths generally in meters. Let's start with the longest, and we'll go all the way across. We'll kind of make a graph here. So we're going to look at wavelengths maybe on the order of 10 to the 4th, or even 10 to the 0. That's on the order of 1. 10 to the negative 4. 10 to the negative 8. 10 to the negative 12. So we're going from some fairly long wavelengths, all the way down to wavelengths that are microscopic, much, much smaller even than that of visible light. Down here with these longer wavelengths, these are what we call radio waves. They're also what we used to broadcast television back when we had broadcast television. We still broadcast radio. Radio waves are fairly easy to manufacture to make in a laboratory. They were the first type other than visible light to be observed by scientists. They're pretty safe. They have really long wavelengths. Okay. The next region is a region, I'm going to skip over, let's see. We go 10 to the negative 8. Right in here is a region, and I'm going to try to get this more or less right, called the infrared. And overlapping a little bit from, say, here to here, we have microwaves. So microwave radiation is not as long a wavelength as radio waves, but the next shortest. Microwaves have lots of applications. Obviously, we use them for microwave ovens, but other applications include cell phone towers. All of the cell phone signals are broadcast using microwave radiation. If we go up a little farther, somewhat shorter wavelengths, we get into what we call infrared radiation. Infrared radiation, notice the word red here, is right next to red at the visible spectrum, but we cannot see infrared radiation. We can sense it, however, just like we can see light, we can also sense infrared. We sense it as heat. If you've ever stood by a fire and you feel heat radiating off away from it, that's infrared radiation. The sun provides does provide all the heat for our planet, and that heat arrives here as electromagnetic radiation from the sun in the form of infrared radiation. Another use you may not realize, but probably you've used quite a bit, if you have a remote control, like for your stereo, your television, remote control signals use infrared radiation. And so do all those radio-controlled toys. Your little radio-controlled cars and trucks and things use infrared. All of these have what we consider long wavelengths. They also have small frequencies. What happens as we go from long wavelengths to short wavelengths, we end up going from low frequencies to high frequencies. So all of these actually have frequencies lower than that of visible light. They have wavelengths longer than visible light, and they have less energy than visible light. So on that ground, we consider these to be the fairly safe part of the electromagnetic spectrum. The tiniest little part of the electromagnetic spectrum, less than 10, it's probably I'll probably do this. There's a little place right in here, little bitty part, tiny in the greater scheme of things. Visible light. We'll talk a little bit more about visible light. But visible light is the narrowest band of the electromagnetic spectrum. It's the part that our eyes can sense. The rods and cones inside of in the retina can actually detect. Okay, so we can detect this part of the electromagnetic spectrum with our eyes. We can actually detect this with our skin, with our hands, because we can feel radiant heat. And those are pretty much the only two parts of the spectrum that human beings detect. It is interesting to think there are other animals that see differently and may be able to see in a different range than what human beings do slightly. Okay. Now, if we go past visible light, the next part of the spectrum, right around here, is what we call ultraviolet. Notice ultraviolet is right next to violet. So this is just below red light, this is just above violet light. Notice when we go from visible light to ultraviolet, we're increasing our frequency, we're increasing our energy, and UV radiation is somewhat dangerous. The sun gives us a tremendous amount of infrared radiation, visible light, and UV. But when we get to UV radiation, it can penetrate the skin more deeply enough to cause skin cancers. And unfortunately, you don't really sense when you're outside UV radiation. You can tell if it's hot. You can certainly see. So there's a tendency to think that when it is bright and sunny, that's the only time UV radiation's out there. But remember, UV radiation can penetrate more deeply than the other two forms. So even if you're not feeling much warmth, you may still be getting quite a bit of UV radiation. If we go up even higher than UV radiation, we get into a region, what we call it X-rays. As we know, X-rays have lots of applications in medicine and even in research and things like taking X-rays of fossils and things. Okay, their value lies in the fact that they can penetrate more deeply than, say, UV radiation. This ability, though, carries with it more risk factors. X-rays can cause cell mutations and genetic problems, damage to genes. And then finally, if we go even higher, we get into gamma rays. Gamma rays are the result of a nuclear reaction, radioactive decay. Gamma rays are the most dangerous of all types of electromagnetic radiation. When you watch movies and you see people with the Geiger counters and things and we're talking about radiation, they're usually talking about in the X-ray or gamma ray type of range. This is the really dangerous part. Notice what's happened. We started off with some pretty long wavelengths, low frequency, low energy waves, and we've worked our way up from radio waves to microwaves to infrared. Finally, a little tiny slice of the spectrum we can see, visible light. Then ultraviolet can cause skin cancer. X-rays can cause other forms of cancer. Gamma rays, very damaging. Lots of forms of cancer related to those. So you can see how things get more and more dangerous. You can also see why. Look how tiny the wavelengths are. If you have a tiny, tiny wavelength, that's small enough to fit inside the nucleus of a cell with a high frequency and wreak havoc on that cell and do damage to genes. This type of radiation, a 20-foot long radio wave, won't fit inside me, much less cause any problems. Okay? Now, in terms of frequency, in this case, the wavelength is decreasing as we go this way. If we come down here and we think in terms of frequency, I'm just going to erase the word light. Our frequencies around here, let me get this in. This is probably around 10 to the 6 hertz. 10 to the 6 is a megahertz. Many of our FM radio stations have broadcast frequencies in the range of megahertz. And they have them in their names. If you're listening to 99.5, that's 99.5 megahertz. They're advertising their broadcast frequency. If you're listening to Kicks 105.1, they broadcast at 105.1 megahertz. So they advertise by their broadcast frequencies. Okay. As we move up here more towards microwaves, we're talking about frequencies on the order of 10 to the 10th. Visible light, 10 to the 14th. Cellular X-rays, 10 to the 18th. And this, of course, is in hertz. So what we see here is that our frequency, which is measured in hertz, is increasing as we go this way. And associated with that is energy. The energy of a wave essentially depends on two things: the amplitude of the wave, which would be the maximum size of the electromagnetic field, the electric fields and the magnetic fields, but it also depends on the frequency. Think about it. It takes much, if you were trying to create a wave and you had a given amplitude, it takes much more energy to have a high frequency wave than it does to have a low frequency wave. So, like I said, that's what makes this end so much more damaging. The energy is increasing, the frequency is increasing, but the wavelength is small enough to fit inside of a cell and wreak havoc, okay? As much as your mom has warned you about don't stand by the microwave, microwaves are not that dangerous. I'm not saying you should climb inside a microwave. You can certainly damage living things by placing them inside a microwave and cooking them. I'm just saying if you're outside the microwave in your kitchen, it probably won't cause problems. Now, if you have a pacemaker, if you have certain medical devices, microwaves can interfere with that. That's why they ask you to turn off your cell phones when you're on the plane. Put them in airplane mode. That's why they will warn people with pacemakers about certain things. Okay, so it's not that they're completely harmless, but I'm just saying, relatively, they have less energy in general than even visible light does. Okay. Now, I want to talk just a little bit more about visible light. Before I talk more about visible light, though, you need to know the order of the electromagnetic spectrum, and there is a way to memorize that order. It's a mnemonic device. Me and one of my classes made it up years ago. Red Martians invented very unusual X games. If you can memorize that sentence, you'll know the order: radio waves, microwaves, infrared, visible light, UV, X-rays, and gamma rays. Okay, so that's just a device to help you remember. The other thing that you should know that I feel like you probably do know is the colors in the spectrum in order. Okay, visible light, the longest wavelengths of visible light start with red light at about 750 nanometers. That'd be the wavelength. Okay, as you go across, and I don't have a yellow marker, so I'll do it in orange, you're going to have orange, yellow. My yellow doesn't look yellow. Green. Whoops, that's violet. Let's get to blue first. Blue, and finally violet. By the time you get to violet light, the wavelength is 400 nanometers. So visible light has a wavelength between 400 and 750 nanometers. Someplace in the middle here, a yellowish green, probably in the neighborhood of 550 nanometers. Human beings actually see best in this kind of yellow-green middle of things than they do at either extreme. We're most sensitive to that. Lots of fire trucks and ambulances are painted red, but in some places they're not. And on the back of many of them, you'll see that yellowy green, that neon green, yellowish kind of color. And that's because that is one of the most visible colors to the human eye. In terms of frequencies, if we can use our laws that we've had before. We know that the speed of light has to equal the wavelength times the frequency. So we can solve for frequencies easily using C over lambda. If we do that, we will find that for red light, the frequency is 4.0 times 10 to the 14th hertz. And by the time we get down there to where we have violet light, our frequency is 7.5 times 10 to the 14th hertz. So you should know the color order of the spectrum. You should understand that red has the longest wavelength, the shortest, the smallest frequency. And if we go across red, orange, yellow, green, blue, and violet, by the time we get to violet, our wavelength is down to 400 nanometers, and our frequency is up to 7.5 times 10 to the 14th hertz. I haven't done a problem like this. It's interesting to think about how fast light does travel and the fact that we can treat light like a wave. Let's just think about, let's do one more problem. When it comes to solving these problems that involve electromagnetic radiation, there's two formulas we use a lot. One is that C equals F lambda or lambda F. That's the same equation we had before for waves, only we put a C instead of V. And second, that the distance traveled by a wave equals the velocity times the time. If we're traveling at the speed of light, it becomes that. So how long would it take light from the sun to reach us? Well, what's the distance from the Earth to the sun? I believe I have it right here in this book. The Earth-Sun distance is let's just go with 1.5 times 10 to the 9th meters. So from the sun to the Earth, the distance is 1.5 times 10 to the 9th meters. We know that the light is traveling at 3.0 times 10 to the 8th meters per second. So the time, if I solve this for time, the time is going to be the distance divided by C in this case, 1.5 times 10 to the 9th. 3.0 times 10 to the 8th. And let's see how long that's going to take. 1.5 times 10 to the 9th divided by 3 times 10 to the 8th. And that is the wrong answer. So now let me see which, I may have looked up the distance, or sun distance wrong. Let me double check here. Oh, yes, I very much did. It's not 1.5. It was 150. Oh, that makes more sense. So let's fix that. That was 150 times 10 to the 9th. Okay. So distance equals velocity times time. The distance from the Earth to the Sun, this is our Earth-Sun distance, is 150 times 10 to the 9th metered. If I do 150 times 10 to the 9th, I'm going to get 500 seconds. So I do 500 divided by 60, comes out to be about 8.3 minutes. It's really funny to think that if the sun were to turn off like a light switch, we wouldn't know about it for 8 minutes. Of course, it'd be a real problem in 8 minutes, but that's how long it takes light to travel from the sun to the Earth. When you compare that, it only takes a little over 1 second from light to travel from the moon to the Earth. That gives you an idea of how far away the sun actually is compared to the moon. That concludes chapter 31, and you should be ready for test 3 as soon as you've finished all of your homework.